Hi, welcome to this video on pseudo-reference electrodes. So I'm going to quickly introduce a true reference electrode in the form of the silver chloride electrode, and then I'm going to talk about the reference electrodes that you often find on screen printed electrodes like this. And I'm going to jump straight into it and go fairly fast, and sort of say, all right, we're going to talk about pseudo-reference electrodes versus true reference electrodes, and I'll sort of start off with a few let's say images. So you'll be used to a true reference electrode. It will look something like this, or you may be used to it. It's kind of got a glass barrel. It has a frit at the bottom of it. It's full of solution, and people use it to to perform experiments like amperometry and voltammetry, and they apply a potential, and the potential is actually applied versus one of these true reference electrodes. I'll also discuss a pseudo reference electrode. As I say, I've got some screen printed electrodes here. I have some screen printed electrodes here. There's a sort of little grey area, that tip there. That's a pseudo reference electrode. So I'll come back to that as part of this talk. So it's not a cell I'm particularly keen on, but people do electroanalytical chemistry in these kind of cells where they'll have something like a working electrode in there, a reference electrode in there, and maybe something like a platinum gauze as a counter electrode. The reason I don't like it is because it's not super modern. Electrochemistry is really good when it's used in point of need testing or is in wearables. So these kind of electrochemical cells make you think that electrochemistry is just this kind of science that really belongs in the lab, and it's not really a science that belongs in the lab. It's a science that belongs in the real world. So that's why, obviously, with my great bias upon me, because at ZP we do manufacture these 501 carbon electrodes, I'm very keen that people use these. But I do want to talk about the reference electrode on these screen printed electrodes, and this is the case for most screen printed electrodes as well, if not all of them actually. So we put a drop of solution on there that makes that an electrochemical cell. We have a working electrode in our classical electroanalytical cell, and we have a working electrode and a reference electrode in our little screen printed electrode, and we have a counter electrode in both as well. So a screen printed electrode is really just a small electroanalytical cell. If we take apart a true reference electrode, that is a true silver chloride reference electrode, we'll find a glass barrel or glass cylinder with something like a porous plug at the bottom of it, or ceramic plug. I'll come to that in a bit. We may have a hole in that cylinder. That hole is pretty useful for getting solution into there, potassium chloride solution, for example, or some potassium chloride crystals. We often have a silver wire running down the center of it. That wire has been chloridized, so we've got silver chloride on it, and we've got a cap on that. So as I say, we've got the porous junction, we've got the potassium chloride solution, we've got the silver chloride, and we've got the silver as well. And the porous junction is to make sure that we've got wet contact with the solution that's being otherwise investigated by something like amperometry or voltammetric technique. And behind that, we've got our potassium chloride solution. So we have our potassium chloride solution, and we're protecting it from the let's say the rest of the experiment through this porous junction. Now if we zoom in on this, we have our silver wire, we have our silver chloride on the edges, on it as well, sitting in a solution. Let's say that solution was 1.0 molar. So we got silver wire covered in silver chloride in a 1 molar chloride solution. That will have a potential that's governed by the Nernst equation, where we kind of say, well, the potential for that reference electrode is its standard potential, which for silver chloride under standard conditions is 0.222 volts, minus 59 times the log of the chloride concentration. Now, I chose 1 molar because it's simple enough that when the log of 1 is 0. So what does that mean then? It means that the reference potential of a silver chloride reference electrode, or true silver chloride reference electrode, is actually proportional to the chloride concentration that you have within the reference electrode. So when it's 1 molar, we'll have a standard potential, as I say, about 0.22 volts. But if, for some bizarre reason, you decided to actually dilute that chloride concentration by 10 times, then you would actually bring the potential there to a new potential. So the chloride concentration goes from 1 molar to 0.1 molar, and actually the reference potential would shift by 59 millivolts. Now, what does that mean when you're doing an experiment? So what that would mean is that you would maybe do the voltammetry on a particular molecule. You would sort of have a true reference electrode in there, and actually you would say, well, right, so the peak potential in this case is 200 millivolts versus the silver chloride reference electrode with a 1 molar chloride concentration. If, for some bizarre reason, you decided to actually dilute the chloride concentration in that reference electrode by 10x, then in fact the potential would shift by about 59 millivolts, and in fact you would then report that, oh, actually my peak potential is 141 millivolts versus silver chloride in a 0.1 molar chloride concentration. I realize that if I just turn these off for a second, I might just run that thought experiment one more time for you. So 200 millivolts because I've got 1 molar chloride in my reference electrode, but if I was to do something, I don't want to say crazy, but if I was to dilute it, the chloride by 10x, then the reference potential would also shift, and then that means that peak would also shift, and that peak would shift by approximately 59 millivolts. We go from 200 millivolts to something like 141 millivolts. So let's just imagine a thought experiment where in fact we were using the working electrode of this ZP501 carbon electrode. We're using a counter electrode of this ZP501 carbon electrode, but in fact we were using a true reference electrode, and we're doing the same experiment again where in fact we measure the peak potential of a molecule, its oxidation peak potential here, and it's 200 millivolts. But then somebody else in the lab does exactly the same experiment, but rather than using the true reference electrode, they actually use the onboard reference electrode. But that onboard reference electrode is not sitting in 1 molar chloride concentration, it's actually sitting in 0.1 molar concentration. So in fact, that person wouldn't record the oxidation peak potential at 200 millivolts. They would actually say, no, it was actually 141 millivolts. It's because you're both using silver chloride, but you're actually in different chloride concentrations. With a pseudo reference electrode, you're actually sensitive to the chloride concentration. Now, this doesn't arise very often as a problem because, in fact, people are so often using a known chloride concentration in their experiments, and they always use the same chloride concentration, and in fact, they always get, let's say, repeatability. But if you just change that chloride concentration one day, then all your potentials could actually shift accordingly. So just know about that. So a true reference electrode, you've got everything kind of locked behind this porous frit. You would run it at a known chloride concentration, and therefore you should have a stable reference potential independent of the solution composition. But if you actually then took a screen-printed electrode and you it was actually at this point be a pseudo reference electrode, then in fact it would be mostly stable, but can be sensitive to the chloride concentration, and that's what I've demonstrated in so far in this video, that you can go from 1 molar and the peak potential would be something like 120 millivolts, 200 millivolts, 200 millivolts. But actually, if you went to 0.1 molar chloride concentration, it would suddenly shift to 141 millivolts. There's a shift of 59 millivolts, reflecting the 10x dilution. I want to just get to the last slide now and say that there are many other types of reference electrodes. You've got standard hydrogen electrode. You'll very rarely use it. It's, I won't say dangerous, but it can be you have to be very careful with it. You very rarely use saturated calomel electrode anymore. They contain mercury. Silver chloride is most commonly used in labs. You may, on occasions, use a copper sulfate reference electrode. So I'll just mention it. This is really used in the kind of oil and gas industry where they want to do sort of protection against corrosion. But what you have is a copper rod sitting in a saturated copper sulfate solution. You know it's saturated because they put some crystals of copper sulfate in there, and they hold all that behind a porous plug. Now I just want to kind of finish with this and say that if you did have any questions regarding electrochemistry and also regarding reference electrodes, then don't hesitate to reach out to us on the ZP website. Okay, let me say thanks very much. Take care. Bye-bye.